Okay, great. So welcome to the ELLIS Distinguished Lecture by Matt Taylor from University of Alberta. Those of us who are working on reinforcement learning, especially multi-agent reinforcement learning and human in the loop in there, definitely don't need an introduction to what Matt is doing. He has background in academia, has worked in the Borealis AI, which is a branch of Royal Bank of Canada, and is now back to academia, and also research director in a startup, AI Redefined, which sounds great. Would be great to hear also of that at some point. And is a fellow in residence at AMI, or Amy. How do you pronounce it?
Amy.
Amy, okay, yes. Where now we were just discussing that, for instance, ELLIS students might be welcome to visit there, which might be an opportunity to some of you guys. But and yes, there's a very important thing in Matt's CV that he was just an opponent of the PhD thesis of Merceline, who is sitting in the back row, and it was really fun to watch today. Thanks for coming, Matt. Floor is yours.
Thank you for inviting me. Yes, man, it's not uncommon for people to say, "Who is Amy? Where is she? I've never met her." No, it's the Alberta Machine Intelligence Institute. So thank you for inviting me here. It was great to be an opponent. I've never been an opponent before, but it was well defended. So today I want to talk a little about reinforcement learning. Those of you who are at this early afternoon's defense are probably already familiar with this, but there's a bunch of examples of reinforcement learning actually being useful. When I started reinforcement learning, it was something that was just fun for video games, but since then, it's been used in finance, it's been used in game playing, for cooling data centers. This is what I had a small part in when I was at Borealis AI. There's now a deployed reinforcement learning stock trading agent. So now I went from video games to helping well-off people become even more well-off. There's some great work from Loom and Google on balloon control. Amy is doing some work on water treatment, so using reinforcement learning to use fewer chemicals and make the water cleaner. And there's some little more recent work on controlling tokamak fusion. So I claim that reinforcement learning is a mature technology that everyone should know about. However, it's still difficult to get new companies or new people to deploy reinforcement learning. So there's a big difference between getting something working in the lab versus getting something that could actually work in the real world as a proof of concept, or getting a minimal viable product. So for those of you who've done some work in industry, when you're thinking about how do I take my cool AI and turn it into something that could actually potentially make me money, not just lose it, that's always a difficult hurdle to get over. So the question is, how do we do this? How do we get from playing games and get into the real world? So today I want to talk about a few different ways of getting there. But one way we could approach this problem is from more of a kind of a business practical standpoint. How do we find good reinforcement learning problems? How do we de-risk them? And how do we get stuff working in the real world? That's not what I want to talk about today. That's more applied. I'd like to talk about some of the more fundamental research that our lab and others have been doing. And I tongue-in-cheek refer to this as cheating. So in a lot of reinforcement learning, if you open the book by Sutton and Bartow, you see the diagram of an agent interacting with the environment and nothing else. That agent is going to go and learn everything for you. But in practice, there's often other stuff. So during the defense, we heard about what happens when there's another person and you need to model them. Well, in addition to that other person, there could be other agents. There could be existing data. We think about maybe automating some kind of plant, like a chemical plant. There's Bob. Bob has been working at that plant for 20 years, and Bob knows a whole lot about how to turn those dials. Why would you ignore all of his knowledge? Well, it turns out it can be kind of hard to get out of him, but if we can get that knowledge, if we can look at the actions he's been taking, we should absolutely do that. and figure out how can we use this existing knowledge or this existing data to learn faster. Oh, another example of this could be Bob's not directly controlling the plant, but maybe there's some PID controllers, proportional integral derivative controllers, or MPC, model predictive controllers. Maybe the engineers have come up with some really smart ways of controlling. So let's use that to get some data and then let reinforcement learning learn on top of that so that we can outperform those. So thinking about cooperative learning. A lot of our group's work has been thinking not just about I could have a single agent in a lab, but maybe that agent could also learn from a human. Or maybe one agent could teach another. Or maybe one agent could teach a human. That's kind of where we'll be going today, those three directions. Instead of just assuming I'm all alone in the world, which is kind of depressing, how can I learn from other agents and people? How can I teach them? So first, let me give some examples for how one agent could help another. Oh, I should also say there's only a few of us here. If you have questions, please interrupt. If you're on Zoom, feel free to raise a hand or just yell out. If you're here in person, same deal. I would love to, I'm talking about cooperative learning. Let's learn together. Don't just have Matt talk at you. So no questions, no comments, okay. So think about how one agent could teach another. Think about offline or batch RL. And I believe I'll give an example of that. Talk about transfer learning or curriculum learning or advice. So we'll go through a few of these examples, how one agent could help another. We could also think about how a human could help an agent. So in Mert's defense, he was talking about how a human teacher could help a student learner. And a lot of these same agent-to-agent interactions could still happen. And then finally, we'll talk a little bit about how an agent might help a human. How if we've got an intelligent tutoring system, instead of just a one-shot, like how to help someone learn how to do a math problem, maybe we could have a sequential decision process where we had a reinforcement learning agent that was acting over time in an environment, and how might that agent help a human learn something. So, I don't have a slide here about reinforcement learning, just to make sure we're all on the same page. In reinforcement learning, we have an agent that's interacting with an environment. The agent takes actions, and then over time learns to maximize some reward. So if I wanted to bootstrap my reinforcement learning agent, one thing I could do is say, I've got some prior agent that's generating data. My prior agent isn't optimal, but doing something. So for instance, I could, I mentioned that stock trading agent. I might be paying someone to trade stocks for me, either a person or an agent. And over time, I'm getting data from them. I'm seeing how they're taking those actions, how they're making stock trades. And eventually I'd like to stop paying them and just work on my own. One way you could do that is off-policy evaluation. So if you haven't heard of this before, this OPE is normally saying, I've got some data, I want to take a policy and figure out how good it is. What if my policy was just always go to the left? How good would that be? What if it was to go left with 50% probability and go up with 50% probability? How good would that be? So if you're interested in these kinds of offline learning questions, this offline reinforcement learning article from Sergey Levine and others, I can recommend. This is a nice introduction to the area. So I can look at a policy and based on data, try to understand how good it is. I could also try to do this a little more theoretically grounded, more guarantees. So with high confidence, I could say I am 95% sure my policy is going to achieve a performance of at least this. So one thing we've been looking at is trying to say, I'm going to get some data, and then I'm going to see what's the best policy I can come up with, and how convinced am I that it's this good? Now, based on this, do I want to deploy it? Do I want to move to the real world, or should I get some more data? So, yes, please.
So we seem to be sort of restricting into the setting where we sort of want the up-to-date agent instead of mixture of sort of like history of agents that can cooperatively figure out ensemble of answers. So I guess sort of question is, why do we only think of this as trying to gather the most up-to-date policy?
Great, thank you. So one thing I didn't mention is right now I'm just thinking about a single agent. So I'm not worried about anyone else in the environment. If there were other agents, I probably would need to keep track of that. I'm also trying to find what's the one best policy I could execute right now. There are cases where you'd want a set of policies to choose from. Right now, I just want to find the best. So I want to figure out how to trade stocks, or another common setting would be more of a medical setting. So I've seen a bunch of treatments for this type of diagnosis. How do I want to act? Or how do I want to encourage the doctor to act in order to maximize the patient's well-being? So if you have data, offline reinforcement learning can be a great tool to have in your back pocket. Let's say you didn't have data. What if you had another agent that could already perform a task for you? This is the idea behind transfer learning. Here's a citation if you'd like to learn it. This is a little bit dated, but if you'd like to learn about transfer and reinforcement learning, this is one survey. And here the question is normally, I have an agent that can successfully perform a task. Maybe they're optimal, maybe they're not. How can I go reach into that agent, grab their brain, and put it into a new agent? Or maybe put it into a new agent with a slightly different task. So back in my PhD defense, I talked about transfer learning between different versions of Keep Away, where these agents were playing simulated soccer. So we super state of the art. We've gone from simulated soccer to controlling physical tokamak plasmas. So that's a pretty good run of 15 years. So transfer learning is great if you can reach into that agent's head and grab its policy. So grab its Q values, grab its neural network, whatnot. One recent work we published was looking at how to do this in a diverse setting. So in this particular case, we were thinking about, I want to learn how to control HVAC, so heating and cooling in buildings, maybe along with putting up and down shades. And I could train in a bunch of buildings in Canada. And I could learn one good policy. Maybe I could learn one good policy per building. But instead, I want to learn a bunch of policies. And I'm going to trade off how optimal they are with how diverse they are. So maybe there's a few different ways I could learn to control those buildings in Canada that are all near optimal. Now I'm going to build some new houses or buildings in Finland, and I want to transfer those policies. So if I'd only learned one policy, I just get one chance. I would just see, does this work or not? But now what we're going to do is build up this whole policy library and do some tricks in order to very quickly say, of these policies that I've learned before, which, if any of them, are going to work well in this new setting? So the question is, can we quickly find a good policy and then maybe continue learning?
So how do you define the diversity here? Do you have any metric that you actually can kind of evaluate your policies?
So it turns out there's actually a number of different diversity metrics. I think the one we used in this case was to say, so let's say I've got one policy, now I want to learn a second one and determine how diverse it is. One thing I could do is look at a trajectory that the first policy recorded, and then take the second policy and evaluate its actions along that same state sequence. If it always took exactly the same actions, it would be identical and no diversity, and you could come up with some way of scaling that between how different the actions that it would take would be. But there are a number of different ways of quantifying diversity that you could try in order to learn this policy library. And we published this in Energy and Buildings, which is a journal I had never heard of before. It's about energy and buildings, if you can't tell. My colleagues who are more into electrical engineering claim that it's a fairly realistic, or a journal that values realism. So again, trying to do stuff in simulation, but hopefully we want to get this into the real world and show that transfer learning can work. So instead of trying to learn how to control a new building over a year or two, maybe we can use just a few weeks. And using just a few weeks of data, we can use one of our past policies and then outperform a hand-coded control problem that an engineer came up with. Or excuse me, a hand-coded control policy that an electrical engineer came up with.
I guess my impression here is that it actually resembles how human operators would actually come up with a blueprint like this. So was the process like you wanted to sort of automate certain elements that were human labor intensive?
So humans can absolutely come up with these, but they are, you're right, they are labor intensive. And our underlying thesis was that reinforcement learning ought to be able to do better than anything that a human hand codes. And that's what we found in practice. We can outperform the hand-coded control policy. And then the related question is, how quickly can we do it? Because if it takes us 50 years of data, then that doesn't really make any sense. So if I want to learn a difficult task, maybe I could reuse some past knowledge. But another way you might say this, maybe if I want to learn on a difficult task, maybe I want to learn an easier task first. So for instance, if I want to learn to move the chair to the blue room, maybe I first want to learn to move to the yellow room, or move to the blue room, or what it means to move a chair. What the heck is a chair? What does it mean to move? So we've done a little bit of work on curriculum learning, thinking about how, if I've got this difficult task, how I can build up to it. And that can be automatic curriculum learning. It could be a person guiding this. It could be a lay person, or it could be an engineering expert, because maybe an engineer can pick the sequence of buildings that are more or less difficult to control fairly quickly. Recently, we had a work on reinforcement teaching, where the idea, I think it's not out yet, but it's at TMLR. And the idea is I've got a teaching environment. So I have a student agent, which could be using supervised learning. Maybe the student is doing reinforcement learning, but then this teacher is changing what the student sees. So in a supervised learning setting, this could be machine teaching, where the teacher is changing which data sets or which concepts the student's trying to learn. In an RL setting, the teacher could be changing which MDP the student is seeing. And actually, over time, this teacher can learn to build good curricula for our students, our student agents. We might be able to use this for human students, probably with some tweaks. We haven't tried it yet. But these are all examples of where, if I have existing data or existing agents, I should probably use them to learn faster. I'll also mention agent to agent advice. So I've got an agent that knows how, I've got an agent from Sony that knows how to clean my house. And now I buy a new agent from Huawei, and this robot comes to my house and they don't know how to talk to each other. Because of course they're different companies and don't want to enable transfer learning where you can just copy one brain. That would be way too easy. But maybe the existing robot could say, go left, go right. Maybe you could give some action advice, some very simple advice. Then there's a bunch of questions. So like, does the student ask for help? Does the teacher proactively provide help? Is there a cost? Is there a cost of 5 cents every time the old robot tells the new robot something? Or is it maybe the old robot can only say 20 things before it gets retired? There's a bunch of interesting questions here. And here's a survey on this, but also other kinds of ways of helping reinforcement learning agents learn, either humans or agents. Let me give one example of this paradigm. This is 10 years ago now. We had a student learning Pac-Man, and we had our wise old teacher, our professor, if you will, who would come in and give advice. And I broke it. Where the teacher would give advice to the agent. And that advice would just be, student, take this action. So only for the current state, just tell the student what it should do. And we can do sorry, PowerPoint trouble. So here we have a learning curve where we have, here's the performance of our student that can learn. And then a teacher comes in and provides some advice, and very quickly, by just giving just a few pieces of advice, the student agent can learn a lot faster. So one thing I want to point out here is we've got, it's a little bit hard to see, but there's kind of a U shape. So the student learns very quickly, then unlearns a little bit, and then learns again. And that's a phenomenon we've seen in a number of different settings that I think, I have a master's student who I think has a pretty good idea of how to figure out why that happens and fix it. So only 10 years after we saw it. Yeah.
How is this meaningfully different from behavior cloning or, imitation learning?
Meaningfully different. So in behavior cloning, typically you have a data set. I would say with in behavior cloning, you typically have a state action data set. In imitation learning, you often have observations and actions that you can look at. And usually you need thousands of those. And here we're talking about, I want to say about 200 pieces of advice. So just very targeted, can I go in and give a very small amount of help to help get significant improvements? And there's different heuristics for doing this faster or better, more efficiently. There's some work out of MIT that looked at how the teacher could learn to provide advice. So in our work, we were just hand coding heuristics for how the teacher could provide advice, but you might learn how to provide advice. So that's kind of cool. But this is still one agent and one student. One of the two papers I wanted to highlight today is this work by Sriram, who's a postdoc at Vector. He's probably going on the Canadian faculty job market in a year or two, but I'm encouraging for him to look outside of Canada as well. This is a joint work with Kate and Mark. And what Sriram was doing is thinking about, what if I have multiple agents and I want to figure out who should advise them or how I should advise them. So if I could have multiple students, and I could even have multiple teachers, figuring out maybe I have one teacher that's really good over here and another teacher that's really good in this other part of the space. Who should I listen to? And one thing to point out, when you're writing a paper and coming up with a new algorithm, please don't call it my algorithm. There's so many times that people don't come out and then you have to say, oh, the algorithm by Taylor et al. In 2011. No, come up with a cool acronym. So the Admiral algorithm. See, good name. So with this algorithm, instead of having a single agent, we're actually looking at multiple agents. So thinking more of a team of agents. So maybe I'm thinking about keep away, got a team of agents, and I want to give all three of them advice at once. How do I figure out where to use that advice, how to use it? So Sriram was one of the first to think about how do I give advice to this team. Another thing is there aren't that many papers that have theoretical guarantees. So in this action advising setting, especially if you have a human advisor, but for now, even with an agent advisor, coming up with convergence proofs can be pretty difficult. So if you're looking for new topics and this is at all interesting, if you're a theory person, I recommend you check out this paper. I'll put up the name again. It's in JAIR, but it's one of the few papers that actually makes some progress on proving that you can get to a Nash equilibrium given your advisor. Given your advisor is giving you suboptimal advice. How can you do that? So I'm not going to go into the details of this one, just keep it at kind of high level, saying there are people who are working on how you advise multiple people or how you could have multiple advisors. So there's a large, interesting area of open research here. That was our first direction, agent. Before I hop into how a human might help an agent, I'm going to slowly take a drink of water, which is a cue that people could ask questions now, including those online if they wanted to. Okay. Then let me start by saying, when we think about a human teaching the agent, there's usually two distinct settings. The first one is if there's no reward signal. So this is typically the case if you're doing behavior cloning. In behavior cloning, you're typically trying to just replicate what the human is doing. And if there's no external reward, it's going to be really hard to outperform the human. Usually the best you can do is just kind of do what they're doing. So let's say there's no reward signal, but then we could do demonstration. We could look at a human's demonstrations and use behavioral cloning. We could have a human give us feedback. Good robot, bad robot. We could also have preferences. So say, okay, human, I could do this, this, or this, which one is better? And then over time, with all of these, you can learn to perform better and better according to what the human wants. So assuming there's no environmental reward, you're just trying to make the human happy. If there is a reward signal, we can use many of the same tricks, but then we could also add in some additional things. So for instance, we already talked about action advice. So this was I give a little bit of help and then the reward takes over, or shaping rewards. So think about in reinforcement learning, sometimes you have a very sparse signal. It can be, or time delayed. And if you can have a human that's giving you these shaping rewards, giving you little breadcrumbs, leading you towards the right solution, if you give them in the right way, you're guaranteed not to change the optimal policy. So a knowledgeable human can provide these shaping rewards, help an agent learn faster, and still guarantee the agent will find the optimal policy. So that's kind of cool. And in many cases, there are some methods where the human doesn't need to be a reinforcement learning nerd. Because ideally, you can have people who are smart, but not computer scientists, still be able to help the agent if they have to understand what a Markov decision process is and what shaping invariant reward functions look like, then you might lose a few people. So helping people be able to, normal people be able to define these shaping rewards is important. Let me zoom into one of these. Let's look at giving feedback. So just having a human saying, good robot, bad robot. First way you could think about doing this with Andrea Tabaz and Cynthia Brazil was just having a human give a number and have the agent treat that as the reward. It worked okay. One of the interesting things they found is that people, despite being instructed not to, because people never listen to instructions, people were giving rewards to the agent for what they thought the agent was about to do. So in some sense, this makes sense. Like, oh, yeah, agent, you're going to, I think you're going to go pick up the milk, which is exactly what I want. That's great. But in a reinforcement learning setting, you want to give rewards for what the agent just did, not what the human hopes it's going to do. So this was an interesting early work that had room for improvement. One of those improvements was the good algorithm name, the Tamer algorithm by Brad and Peter. There, they were saying, I'm going to have a human that comes in and again gives numeric feedback, but this numeric feedback is going to be a proxy for the return. So in reinforcement learning, you get a reward signal. The agent's ultimate goal is to maximize this total reward. The return is that sum of the rewards. So if the human is giving feedback that's correlated with the return, then really what happens is this human is giving feedback saying, is the action you just took the optimal action for the policy I want you to learn? So now instead of reinforcement learning where you have to balance exploration and exploitation, now the agent just has to do supervised learning. The agent just needs to figure out, am I going to take an action that will get the human to tell me, good job? And using the Tamer framework, Brad and Peter were able to teach a Tetris agent to learn very high performance Tetris, again, with only, we're talking tens or hundreds of pieces of feedback. So instead of training for thousands of steps, the agent can learn very quickly because so much knowledge is contained within this piece of feedback. Are you acting optimally right now or not? So Tamer is learning, the human is giving a return. But that's just how the algorithm treats it. It really, in both cases, the human's giving a number and the algorithm's deciding what to do with it.
How is it different from, let's say, reward augmentation? Essentially, you're just adding, let's say, additional kind of reward to an existing given reward function, right?
So if we were doing reward augmentation, then that would probably be more like this first one, where we had an environmental reward and the human was giving an extra reward. One thing I didn't make clear is in these works, we're assuming there's no environmental reward. So we're just left with what the human tells us.
So you expect to learn purely from human feedback? Is that
Exactly. We're trying to learn just from the human. Let's not even worry about the environmental reward yet. So the human's going to give some numeric feedback. We could treat it as a reward. We could treat it as a return.
Yeah, so regarding to this, I assume that this kind of feedback is actually given for each, let's say, time step. So as humans, sometimes you might lack of like future vision of how this action could affect your ultimate outcome. So how would you solve this kind of issue? Is there something better if actually get it solved in this?
So there's at least three questions in there. So the first question is, what happens if the human is suboptimal? Well, so if there's no environmental reward, you're probably out of luck. You probably just have to do what the human's going to do. The second one would be, what if the human is optimal, knows the optimal policy, but isn't quite getting it because they're confused, because there's noise, because they're clicking the button not quite fast enough. And then we're going to be suboptimal. So we can try to push against that, but we're probably going to be strictly worse than if the human's perfect. And then the third thing was, I don't remember.
But what if your like a reward is like myopic instead of?
Oh, right. Yeah. So what if the human isn't looking to maximize the rewards from now until the end of the heat death of the universe? What if the human's only thinking about for the next 10 seconds? And in that case, the human's going to have a very myopic policy, which the agent's probably going to be stuck learning. Unless, going back to Mert, I could think about if I had a model for how the human was suboptimal, if I could try to model that their discount factor was too low, and then go back and kind of unroll that up into the real problem. But I don't think anyone knows how to do that yet.
Yeah.
If you have ideas, we should talk. Humans giving a number, we want to do something with that number. Tamer, awesome algorithm, cool name, even better algorithm, even better acronym. Oh no, this wasn't the one. This one's an okay acronym, SABLE. It sounds kind of cool. With SABLE, what Robert was doing was saying, if a person's saying good dog and bad dog, does that really mean -2 and +6? So instead, Robert took a Bayesian approach, saying, can we maximize the chances that the policy we're going to follow is consistent with the observational history we've seen? So this was an improvement over Tamer, because in some cases, because we could show that, well, we don't need to treat them as numeric rewards. We can just say good dog, bad dog, and figure out what that means. Also, importantly, we could also figure out, what does no feedback mean? So how many people here have trained a dog before? Oh my gosh. You people don't like dogs. I was on a walk the other day. Everyone had a dog. Well, okay, so when you train dogs, typically you reserve the negative feedback for rare instances. Like, you're really not supposed to hit the dog with a newspaper. That doesn't work. Instead, what you do is get the dog to do something good and then reward it with a treat. If that's your main training method, then a lot of the time you're not giving the dog treats, which means a lot of the time, if you're not saying anything, that means the dog needs to keep exploring and try to figure out what you want. So if you're a dog trainer, you may often just say nothing while the dog figures out how to respond to you. If you are a vindictive grader with undergraduates, you might go through and get a real kick out of taking your red pen and marking these big red X's on everything that the undergraduate gets wrong. And not writing that X could actually mean they did the right thing. So in Robert's, Robert Lofton's Bayesian framework, he could figure out what no human feedback meant. Now for the better algorithm name, from Sable to Coach. So we published Coach at ICML. We put in the camera ready, and then someone wrote, "We just had a new algorithm related to teaching. We named it Coach. Can you please name your algorithm something else?" It's like, oh, dude, I'm so sorry. So cool algorithm name. There's a few coaches out there, go figure. And the idea behind Coach is that people may not actually be giving feedback on what the agent is doing. People may be giving feedback on how the agent's policy is changing. So here, think about, we've got this, our cute dog, and our dog needs to get to the goal state in yellow. And people have this slider where that goes down to shocking the dog on the dog collar. Don't do that in real life. Saying bad dog, saying good boy, or giving the dog a treat. My dog is super food driven. She will do anything if she could figure out how to get treats. So one thing the dog might do is go straight to the goal over the grass. That's not great. Another thing the dog could do is not go over the grass, but take the long way around. So getting there, but not optimally. The optimal path is to avoid the grass and get to the goal. So let me give some examples from the human subject study that we did. So we've got our dog, and let's say the dog goes straight across the grass. We'll say that's the bad case. And then I already said, here's the all right case and the optimal case, or the good case. So now we're going to have three conditions. Human comes in, gets put in one of these. The improving condition is the human sees the dog go across the grass, and then do this all right thing. Steady condition is the human sees the dog do the all right, the all right, the all right, and then, as in the first case, they can give one piece of feedback at the very end. And then in the degrading case, they see the dog do good, good, and then all right, give some feedback. And what we see is that in the improving case, people give higher feedback than in the steady or degrading. So remember, we're asking people for feedback. Give the dog feedback on right now, right after they execute the policy. So people are seeing the same policy, but giving different feedback based on what came before. And you might look at this and say, Matt, this is obvious. People are giving the dog feedback based on whether it's getting better or worse. And yeah, that does seem kind of obvious in retrospect. And it turns out when you use this, when you say the person isn't giving Bayesian feedback, they're not giving rewards, they're not giving a return, they're giving the advantage. Another reinforcement learning concept. If you say, well, people are giving the advantage function, then in fact, we can learn faster in some settings. The real reason I wanted to show you this was not because, look, people have come up with different ways of people teaching agents. The real message I wanted to show here is people have come up with different ways of interpreting human feedback to agents that seem reasonable and can come up with human subject studies showing it works. We don't really know when one of these methods is going to be better than another. If we want to deploy a robot, if we want someone to bring home a 5,000 euro robot, and I want my dad to be able to teach it, which of these algorithms do we want to use? Or none of them? Is there a fifth algorithm that's even better? We don't know. And this is not just, I think this is not really a job just for the computing science nerds. I think this does involve psychology. I think this involves cognitive science. This might include teaching people how to teach robots. Maybe we want a user guide to say, if you're giving if you're giving an advantage function, let's teach you what that means. Yeah, Mark.
Do you think there's a possibility of something like a master algorithm like Edge to play these three algorithms?
It's always possible. So one thing let me rephrase that a little bit. What if we had a master algorithm that did this and some other things, got a bunch of human feedback, and then said, Coach has this policy. Sable has this policy. Now, human, which one of these is what you meant, if any of them?
See,
Yeah. So then, and then they can say, oh yeah, this is exactly what I meant. Then we're golden. Chances are though, we're gonna take our master algorithm, learn 15 different policies, bring it to the human, and you're like, I mean, 2 and 16 were kind of close, but not quite. So then there's probably some iterative thing we need to do. All right, so I was focused on no reward signal. You also could have reward signal. Last thing I really wanted to talk about here was saying, I often think about how could my dad teach a robot? But what if you had a subject matter expert? What if you had a programmer? So with Israeli colleagues, we ran a study with master students who are partway through their first AI course. And we had them write functions in Python or Java. I think it was Python. Write functions in Python to help agents learn faster. And it worked. Not super surprising. You would hope that smart people could help agents learn, but these were people who were not AI experts. They had, I think they had 1 or 2 lectures on reinforcement learning. So it's that in between. If they're not a complete layperson, but they're not an ML nerd, how can we get useful information out of them? Maybe they could write some code. So the last direction I'll talk about, just to wrap up, is say, well, what if we've got our agent could learn from a human, our agent could learn from a person. What if our agent could teach a person? And this is where intelligent tutoring systems could come in. So we're presenting a paper at AI Ed this summer, looking at how to try to help people learn to solve an MDP. So figure out how to give them support so that they can more quickly learn how to, in this case, it's kind of a navigation-like task. So here we're working with Carrie Demonzep, who's a human-computer interaction person. She's awesome. We're doing these more lots of human subject studies showing statistical significance. That's cool. But let's take this into the real world. Similar group of people, slightly a few more. Here we're working with a company where they're saying there aren't enough pilots now certainly in North America to train the next generation of pilots. So instead of thinking about how can a human student fly an airplane with a very expensive, very skilled, expert flight trainer, what can we do in simulation? Well, one thing you could do is just have people mess around in simulation. That's perfectly fine. But wouldn't it be better if we could provide them some support? What we try to do is have an AI teacher that can help give feedback to students. So where did this teacher come from? The teacher could learn using reinforcement learning. In our case, we used a human expert, human pilots, to teach our agent. And now our agent can say, hey, student, you're messing up. You could do a retrospective and say, hey, student, you did mess up. Let me go and tell you, oh, at time step 33, you should have done this. Here you can see we're giving some fairly simple advice in real time. What I'm really excited about is, can the agent look at the student and say, wow, I'm not sure Matt should be training to be a pilot. He is so confused. Human expert pilot, please come over and help Matt. He's not going to figure this out on his own. So I think there's lots of different things that we could do once we have a trained AI teacher in the loop. And if this works with 1 student, it could also work with 50 students in parallel. So this is where you get the scale up. Think about how do we get a bunch of students training in simulation so that when they go up one-on-one with the real expert pilot in the physical airplane, they make the most out of that super expensive training time. Yeah.
Is there any information flow from students back to the teacher in this year?
Not yet, but why do you ask?
Because seems like a waste of a lot of experience if you're not taking advantage of mistakes that students make and they're like objectively just determined by simulators somehow.
So we're definitely collecting a bunch of data. And one of the things we'd like to do with that data is in different scenarios, find different common ways that students mess up. And the pilots already have a lot of this knowledge in their head, but they may or may not be able to enumerate it. So if we do a bunch of data mining, we might be able to figure out, oh, actually in this climbing task, often students overshoot. They climb too high and have to come back down. And if we can do that automatically for a bunch of different tasks, then we could ultimately improve the teacher. But that's a much slower human in the loop before we update the teacher. If we could do that, then we might be able to update the teacher online eventually. Was there, no, you?
So the teachers pre-train, let's say beforehand, and you just plug in to train the students.
That's right. We get the teacher to train a bunch in the simulator and with the human expert. And then